response and ramp response of average. So I'm going to use this one. Okay. Okay, now let's consider the interconnection of systems. Okay, now let's consider we have, say, two systems. This is H1 and this is H2. So both H1 and H2 are impulse response of the system. So H1 of T and H2 of T, they are the impulse response. Of each system. Okay? And then the y of t is equal to ready for this y1. And this is y2. So very easily you can see that y of t is equal to y1 of t plus the y of t, the sum of these two outputs. And what is the y1? Y1 is the output of H1. Now, since H1 and H2, they are the impulse response, so we can write the Y1 as H1 counterweight X of T. Okay, this is the definition just here. Negative infinity and positive infinity. X of tau, H of T minus tau. Okay, let me write it up here. Okay, H1 convert X. So that's the definition of convolution. Okay. Plus H2 of T, H1 of T, convoluted T, H2 of T, convoluted X of T. So we can take X of T out of the summation. So what does that tell us? This tells us this connection can be equivalent to by X of T and then Y of T. The system is simply H1 of T plus H2 of T. This means they are equivalent. They are equivalent. Okay? So this is the equivalent system, H1 of T plus minus H2 of P. And also, we have another configuration. Now we have two systems. They are in series connection. We call this cascade. And this is the parallel connection. Okay? Sometimes we call the output from the Z, from the H1 of T, the Z. So from this configuration, we know the Z of T is a convolution. Okay? And the Y but that also equals to H1 common X of T. Now, since there's a property for the convolution is associative. Okay, we use sorry. So this is equal to H2 convolute. And then convolute X of T. So this is equal to H2 convolute H1 and then convolute X of T. Okay? So this is equivalent to now, there's a question here. I did not prove it, so this becomes your homework assignment this week. Okay, so prove. H2 of T common H1 of T common X of T actually also equals to H2 of T convolute H1 of T and then convolute X of T. Okay, so your homework assignment number 5, okay, show that okay? You can find a solution from anywhere, from any book. Start from definition. Start from the definition of convolution. Okay? Start from the definition of convolution. Find the solution from any books or any resources, and I will give you the answer next week. And I will upload the answer next week. Hopefully, you can find it very easy. But this is an important property. Convolution is associative, so you can change the order of the convolution. Maybe let me give you another one, which is also very easy. Okay? Prove this one. This is the second one. First one, prove that H1 of P over H2 of P the same as H2 of P over H1 of P. Okay, prove these two equality. Because these two are the fundamental properties of convolution. Okay? So this is your homework assignment for this week. All right, another one, feedback connection. We have seen this one in the first week. Now here we have H1 and H2 of T, but we put H2 in the loop, in the feedback loop. We call this the feedback loop. Feedback. So this is the feedback loop. And since we put the mic side, so this is called the feedback. Because we put the mic. There's another one called positive feedback. That is we replace the minus sign of positive sign. Okay, here we use the negative feedback. From the configuration we have while P ELT is called the error signal. And the error signal comes from the input x of P minus the feedback. Okay, that's equal to H2. Comma. 1. Okay? So we can combine these two. So while P is equal to H1 of P comma x of P minus H1 of H2 of P comma 12. Okay, so now the H1 of P comma x of P and then minus H1 of P comma H2 comma 12. Right. Okay, if I call this entire B so that means we are going to find this equivalent system. So this equivalent tells us y of P output equals the solution h of P and the input result. So now I'm going to replace the 1 of T by h of T comma the x of T again. So which implies the output is equal to minus so now I get x. The equivalent system. The equivalent impulse response is equal to 1 minus 1 common with 2 and then common with 2. So you look at equality here. H of P on the left-hand side. And the right-hand side. This H of P appears in both sides of the equality. So this is an implicit. This both I don't know how to solve it, honestly. It's very difficult to solve it in general. So this kind of approach in practical, we don't use this approach in engineering problem. Okay? Instead, we are going to use the S-domain Laplace transform later on. So Laplace transform is the technique we use to solve the interconnected system like this. Okay, so this is impractical. Not good. Theoretically, it's good. This one? It's not from here. Just assume. Let me call this. We assume this is your T. Just give it a name. This is a signal. This one is a signal after the summation. We call that ELT. And this ELT is equal to the input X of T. Okay, this side, right? So this is X plus X of T and then minus. Can I call this a okay. Output of H2, okay? Then the ELT is equal to positive plus X of T minus. Okay? And this Y2 of T is the output of H2. And this Y2 of T is the output of H2, which is equal to convolution H2 E. Okay? Again, even though you have a equality for the equivalent system H of T, but honestly, I'm not sure how to solve this very efficiently or analytically. Okay? Because we never use it. In a practical engineering problem, we never, or I seldom see anyone use this technique to solve the problem. Okay? So it's just a solution, mathematical equality, mathematical solution. Alright? Okay. So that's why later on we have to introduce another technique, we call it Laplace transform. So we are going to transform the convolution, the integration into the S domain Laplace transform. Okay? All right. Question? So use Laplace transform instead. Okay? All right. Now, in the next slide, we have an example here. It's a series connection of an averager and this is differentiator. We call this differentiator. Averager and differentiator. Averager is in this one. In the previous slide, in the last hour, now you see. Okay, this is the averager. Okay? We've done this one last time. So this time, let's consider the connection, the series connection of an averager and a differentiator. So this differentiator, the structure is very simple. It is the sum of the signal minus one step delay of the signal, and then divided by the time step delta. So if you have a So suppose you have a unit step input. Usually we use Z inverse to denote the delay. Okay, suppose we have an input X of t here. For the moment, the input is Z of t. Yeah. Okay. Now, if my input is a unit step, by the way, there's a product here, so times 1 over rho. So the input V of t is equal to X of t minus X of t minus one step delta, and then divided by the delta. Okay, so this is the V of t. Now, if the input X of t is a unit step, so what do I have here? We have unit step. X of t, the magnitude is 1. And then we have another one step delay. Okay? That'll be t X of t minus delta. The delay time is delta second. So the difference between these two signals, okay, this guy minus this one, okay? So now you have a rectangle signal. Now, the magnitude up to this moment is 1, okay, because we are considering the difference of two unit step function. But then we have to multiply it by 1 over delta. So you multiply it by 1 over delta. So now, here, right? Now it is D of T. So if your time step is very, very small, then you height or the function value of D of T becomes very big. So this approximately equals to the delta function. Okay, actually we use such delta. It's a delta function actually. We can approximate the delta function by using the differentiator. Now usually this is also a numerical technique to generate a delta function. Okay? And then we have another one which is an average one. Okay, so this is the average. So now we are going to connect these two systems. So we are going to connect these two systems. So this is equivalent to this one. And then you repeat that again. Yeah, maybe let me shift this a little bit to the right. Maybe that's better. Yeah. Okay, so this one is the this. So we are going to the system to your T side differentiator. Now, what is the purpose of this example here? Now, I have and both are linear systems. And in both are linear systems. Okay? So which means from the previous result, we know that for a linear system, we are able to interchange the order of the connection. So I can put the average first, and then put the differentiator later. And these two are equivalent. These two are equivalent. Okay? Alright, and then let me go back to the slide. So what can I do with this structure? So now I have average first and then differentiator later. Now there's a reason for doing this graphically. Before we move on, go back to the example. Usually, if you put a differentiator, not a signal, there's a problem you have to consider. If the signal has a noise or has a discontinuity, like there's a jump, for example. Right? If we consider a unit step function, there's a jump, there's discontinuity over here. If you differentiate the function right at this moment, you will have a very big problem, numerical problem. You are going to encounter singularity, right? Because this is a discontinuity. You will have a singularity problem, numerical problem. That's a big issue. So to avoid that problem, we can switch the order of these two components or these two systems. You put the average first. Okay, so we try to compute the average value of the unit function first. So you have a much smoother function. After average, you have a smoother function, like I showed you last time, right? Okay? Remember the figure that I showed you. These signals, you can see that there are lots of kind of noise. Just jump up and down, jump up and down. Okay? If you try to differentiate a signal like this, you will have a very big problem, numerical issue. You are going to have very huge number. You are going to have overflow sometimes. Okay? So how do I avoid this kind of problem? If we can switch the order of the operation, we use moving average or average jump. So you can see that the output becomes much more smooth. Okay? The green line is much more smoother than the original signal. This is the moving average of the signal. If you differentiate the green line, you will not have a problem. If you differentiate the signal directly, you will have a numerical issue. That's a big problem. So that's why, for this example, we switch the order. So if you switch the averager with the differentiator, we take the average of the input signal. Now the input signal is unit step. So after the averager, you have the output like this. Okay, we have seen this one last week. This is the output after the averager, if the input is unit step. Okay? And then we apply the differentiator. Again, remember, this is an approximation of the differentiator. So the output after the differentiator will be this trapezoidal shape function. So this is the output after the differentiator. Now, if you let the delay smaller and smaller. What do you have? Look at this figure here. Okay, I think you can still can see it. If you let your delay time smaller and smaller, then the slope will become bigger and bigger. So more and more like a real impulse response of the average. Okay, if you go back to the again, let me lower down the last week we have considered this impulse response. Now this is the impulse response of the average. The input is a real impulse, but numerically or theoretically, theoretically we can do it, but numerically we cannot do it. So that's why we have used the approximation, the differentiator to create, to generate the impulse. Okay, so when the delay time becomes smaller and smaller, the trapezoidal shape will be this is the trapezoidal shape. If the step, delay time, the time step is smaller and smaller, okay, this will be more and more like a rectangle. Okay? So that's the way that is the way we use to generate the impulse response of a differentiator. I'm sorry, of a moving average, or average. Got it? Okay, clear? Is that clear? Okay, let me summarize what we have here. The purpose here, okay, let me write out this one. And average. This, so called this, the moving. Okay. Okay, only an approximation. So that means if you use the schematic to represent this, to express this will be ideally I need an impulse or an input. Ideally I need an impulse. key, individual key. Individual key, yeah, individual key. Okay, individual key. Okay. Here. Very good. But this is very difficult to generate because we need infinite amplitude of the signal. So instead, we use this to approximate. So let me call this, this is equivalent, yeah. Theoretical, it is equivalent. Equals. But again, this pure differentiation of a unit step is also impossible. Okay, so we are going to using okay. This is an approximation of, okay? But if you differentiate the function directly, usually you will cause a problem because you are going to amplify the noise. We don't like that. So instead, we switch the order. Okay, so this time we go through the average of Now, again, here the reason why I can switch the order because both of them are linear systems. Because they are linear systems, so I can switch the order. Because I can switch, because of the reason I just mentioned. They are linear systems, so I can switch the order. Because they are linear systems. Okay? That is an important concept here. So this is the field of T, the time interval. This one will be T. Okay? And then H the delta will be very similar. E plus. So when the delta becomes smaller, 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 this function will be very close to the ideal impulse response of the area. So that's the main idea of this exam. Okay? Again, one other point here is we don't like to use differentiation right after the signal. Because this will cause singularity. This will amplify the noise. Will cause singularity in many other cases. Will amplify the noise. Okay? All right. Any questions? Yeah.
Why the differentiator is zero?
Say that again?
Why the differentiator is zero?
Differentiation, because this is differentiation, right? Differentiation. For example, suppose you want to differentiate. Here's over dt. What is the definition? That is the difference goes to 0. T minus x of t minus 2. And then divided by the field. That's a slope, right? If you have this. So this is T, and this is T. So this function value is x of T, and then this function value is x of T minus 2. Right? So this is the interval here is still. So the slope is a difference divided by the width, the interval. Okay? So this is the definition. Now again, this is the theoretical value. We have to take the time interval becomes smaller and smaller and smaller. But practically it's impossible. Okay, we can only choose a small number, a small enough number, and that's it. Okay? Alright, any question? Yeah, that's a good question. Any other question? When we are dealing with signals, there are lots of practical issues we have to take care of, we have to take into account. This is one of them. Okay. All right, let's take a